This is Physics Educational Technology, or PhET, which has the circuit construction kit, and these are free online, and these are really great. So I put a battery here and a lamp. I'm going to grab a couple of wires. And as soon as I connect them, notice I don't have a switch in here, but I'm just going to connect them. Then the light bulb, of course, starts glowing, and we see these electrons running around. Well, we can see that that depends on the amount of voltage that I have. Whoa, and I just started a fire. Okay, let's not do that. And so the larger the voltage is, the brighter it is, and the faster the electrons are going. And the smaller the voltage is, the less the electrons are going and the fainter it gets. Also, when I measure the current here, I'm going to change this one here. So notice that when I change the resistance here, when I increase the resistance, the current will go down and the lamp gets fainter and the electrons slow really down. That's what the current means. So that, and then when I go the other way, I decrease the resistance, then the current goes up and it gets brighter. So for larger voltage, the power goes up, and for larger current, the power also goes up. And that's reflected in this power law over here, which says voltage times current. By the way, we use intensity of electrical current. So I, because apparently the C was already taken up for something else in electricity. So voltage times intensity of electric current, or just current, is the power. And we just saw that the larger the voltage is, oops, hold on, that's actually the resistance. So the larger the current is, I show that right here, the more power, and the larger the voltage is, the more power. The resistance is related in a different way with these. So when I increase the resistance, notice what happens with the current. Then the current goes down. That's reflected over here. So they are inversely proportional to each other, or indirectly proportional to each other. So the larger the resistance, the smaller the current. Or the smaller the resistance, the larger the current. So we're comparing these numbers here. When this goes down, this goes up. Resistance is going down, current is going up. Or the other way, resistance is going up, current is going down. So voltage and current combine in two different ways. We divide them, we come up with resistance. We multiply them, we come up with power. And we just need to keep that in our minds as we proceed. All right, I prepped this particular one in such a way that I actually want to have 9 volts on this one here. And I want to have 1 ohm on this one here. And this one is pretty bright. I'm going to put the current meter on it, or the ammeter. And now I have 9 amps and 9 volts. I multiply them. I come up with 81 watts of power. 81 watts of power. All right. I have a second light bulb, and we will look at its brightness momentarily. Notice that its resistance is different, 3 ohms instead of 1. And notice it's quite a bit fainter. So when I measure it here, I have 3 amps and 9 volts. So 3 times 9 is 27 watts. Now, around the house, light bulbs, in fact, any kind of electric devices are always wired in parallel. And that's what I'm going to do here. And we will see in a little while they're wired in parallel. And this was what parallel means. They're actually parallel to each other. So as the current runs through these here, it actually runs through both, and then they have a certain amount of voltage. If one of these goes out, notice that the other one is still going. Disconnecting this one here would be a little bit harder. Let me try it. Now everything goes out, but notice if I reconnect them here, then yes, this one is disconnected, but the other one still goes. That's the reason why we wire things in parallel. If one of them goes out, the other one should stay on. So I'm going to reconnect them both here, and we can see that this one here, of course, gets 81 watts, while the other one, oops, not what I meant to do, gets 27 watts, which is, by the way, harder to see. I actually would have to disconnect this one here again, but we saw it earlier. So here we go. There's that 9 times 3, 27 watts. Okay, so this is when they're in parallel or when they are single. The one with the higher resistance draws less current and is therefore fainter, while the one with the lower resistance draws more current and is therefore brighter. So a brighter lamp has less resistance. Okay, now comes the interesting part. I'm going to wire them in series with each other. So I'm going to connect them here and here in just a moment. And remember, this one is the brighter light bulb, right? This one is the fainter light bulb. And there we go. This one has become the brighter light bulb. What happened? Well, what happened is that because they're in series now, actually they both they both push the current down to only 2.25 amps, and then they share the voltage. For that, I actually need a voltmeter to put it on both of them here. Notice that the total is 9 volts, but they have to share it now. So this one up here gets 2.2 volts and 2.25 amps. And when I multiply the two, I come up with roughly 5 watts. The other one, that's why it's so faint. You know, earlier it was 81 watts, I think. This one here gets more voltage due to a larger resistance in series circuit. It gets more voltage. So here, this one gets 6.7 volts times, it's still the same current, no matter where I measure the current now, it's the same. So this one here gets 6.75 volts times 2.25 amps, which is about in the neighborhood of 15 watts or so on. So when the two are in series, they have to share the voltage, and they both turn the current down, so they both get less energy and power, but it's the one that used to be actually the fainter light bulb which is glowing brighter now.